Hi everybody. This will be the first video for Chapter 15. You'll see a series of videos. Look at the beginning page number for each one. In Chapter 15, we introduce the concept of chemical equilibrium and how it relates to free energy. This is the homework that is there for practice, and you'll see these unusual homework, their VC, their additional homework problems in the textbook. When we talk about equilibrium, we talk about a reversible process in a system where the forward reaction and the reverse reaction are going at the same rate. So in a generic situation, we have reactants in equilibrium with products. Now in the textbooks, you'll see this funny looking double arrow here, but you'll see me write it like this because that's the only way I could type it in Word. And remember, it's important that it's the rate that's the same, not the amount of reactant and product. When we get back into class next week, I'll show you a demonstration that I think will really illustrate this for you. So let's just think about some generic equation. We have D plus E reacting in equilibrium to make F and G. And we can use the lowercase d, E, F, and G to balance our equations. So the law of mass action can be written as follows using the coefficients in the balanced equation. But in this case, these things are either aqueous or they are gases. They are not pure liquids and they are not pure solids because we don't include solids and pure liquids in this expression. We'll talk about the reason for this later, but the reason is because the concentration of solids and liquids does not change. And we're looking at concentrations when we start plugging these materials in. So we can write the mass action expression. Q, the reaction quotient, is equal to the concentration of F, one of the products, raised to the little f power, times the concentration of G, raised to the little g power, divided by the concentration of D to the little d power times the concentration of E to the little e power. So you see what we've done here is we have plugged in Q is equal to the concentrations of all the products raised to the power of their coefficients in the balanced equation divided by the concentrations of all the reactants multiplied together and raised to the power of their coefficients. And when we calculate this, we call it the reaction quotient Q. And Q can be calculated at any time. Most of the time as we talk about this, we're going to be talking about systems at equilibrium. So we'll be used to saying it's the equilibrium concentration. But in this situation, it's really just the concentration at the time that we're doing our measurements. So now let's look at a real system, an actual chemical equation instead of the generic equation. If we're thinking about this reaction where we form hydrogen iodide, we have hydrogen gas plus iodine gas is in equilibrium with 2 hydrogen iodide gas. So we look at the coefficients in the balanced equation. Remember, if there's nothing written, that means there's a 1 there, it's not a 0. And we have 2 hydrogen iodide gas. So we can write our mass action expression. Q is equal to the concentration of the hydrogen iodide squared, because I have this 2 in the balanced equation, divided by the concentration of the hydrogen gas times the iodine gas. Now, when you think about this, we're talking about these concentrations in moles per liter. So we'll have moles per liter, the quantity squared, divided by moles per liter times moles per liter. So in this case, the units actually all cancel and we don't have any units. Depending on what these coefficients are, we might have all kinds of weird units. We could have moles per liter raised to some power, x and x, or we could end up with liters per mole to some powers, just depending on what these coefficients are. So there are units for some of these equations, but sometimes there are no units because they cancel. So in chemistry, we just tend to ignore them. And you'll see me writing Q or K values later with no units, and that's okay. Now this Q can change as the concentrations of the products and reactants are changing. Q becomes a constant once we reach equilibrium. And since the concentrations are no longer changing, we just call that constant K. And when we're dealing with concentrations in moles per liter, we call it K sub C. So let's go ahead and look at a situation now where this equation has reached equilibrium. So now instead of Q, we can write K sub C, our equilibrium constant, is equal to the hydrogen iodide constant squared divided by the concentration of hydrogen times the concentration of iodine. And if you look at this, it's identical to my Q, but we've replaced Q with K sub C. Now, the really important thing is to make sure that you always balance the equations before you start writing. So let's look at another example. Write the equilibrium law for the formation of ammonia gas according to the following equation. Nitrogen plus hydrogen makes ammonia. The first thing you always want to do is check and make sure these are balanced, and this one is not. So we'll balance it, 1, 3, and 2. Now my equation is balanced. I can go ahead and write my equilibrium expression. K sub C is equal to the ammonia concentration squared divided by the nitrogen concentration to the first power, and I usually leave that out, times the hydrogen concentration cubed. Now, if you look on the next page, I want you to go ahead and take a few minutes, pause the video, and then go ahead and work these out. So go ahead and you take a minute, pause your video, and write the equilibrium expression for both of these. Did you get the same thing I did? For this first one, K sub C is equal to the oxygen concentration cubed divided by the concentration of ozone squared. And for the second one, K sub C is equal to the concentration of this crazy complex ion, Ag NH3 with a positive charge, divided by the concentration of the silver ion times the concentration of the ammonia squared. So this is the end of the first video.